Class 22, implicit functions. All right, so I have this curve, this red curve here. It is given by the equation x cubed plus y cubed equals 3xy. So trying to solve that equation to make it look like y equals is difficult. It's kind of a pain in the butt, or maybe not even possible. But I want to find the equation of the tangent line at the point 3/2, 3/2. So 3/2, 3/2, it's right here. So I'm looking for the equation of this tangent line. So I need two things to find the equation of a tangent line. What do I need? Slope and a point, and y-intercept, which I can find by using a point. So I have a point, 3/2, 3/2, that's on my line. And I need the slope of the line, which I find by getting what? The derivative at the point. Okay. So I need dy dx at the point 3/2, 3/2. So I need dy dx evaluated at the point 3/2, 3/2. So when you have a formula that's defined implicitly, that is, you can't solve it for y, then we have to use a little bit of a tricky approach, a little bit sneaky approach to try to find dy dx. And my approach is going to be to take dy dx of both sides. Okay, so I write my equation down, and I want to take dy dx of x cubed plus y cubed equals dy dx. Sorry, d dx. What am I doing? D dx of 3xy. That should just be a d dx. What I'm taking the derivative of. So if I write d dx of this stuff, that means take the derivative of this stuff. Dy dx means the derivative of y with respect to x. But I want to take the derivative of x cubed plus y cubed. So dy dx is like, if I write dy dx, that is d dx of y, right? So it's a shorthand, dy dx is. Okay, so I'm going to take d dx of both sides of the equation. So let's start with the left side. That's two functions added together. So that means that that's two separate derivative problems. So start with the first one. What is the derivative of x cubed? 3x squared. So the derivative with respect to x of x cubed is 3x squared. Okay. Now I want to take d dx, right? So the derivative with respect to x of y cubed. So what's the derivative of y cubed? 3y squared, right? But y is a function of x. Okay, so I want to take d dx. The variable that I'm taking the derivative with respect to is x, not y. Right? So d dx of x cubed is a straightforward 3x squared. But d dx of y cubed is going to be 3y squared times the derivative of y. Why? Why do I have to multiply by y prime here? It's the chain rule, yes. Y is the stuff. So imagine that I could solve this thing for y, right? My original equation. If I could solve it for y, I would have a function y of x equals a bunch of stuff, right? So y is a function of x. So if I want to take the derivative of y, then I would take, so if I want to take the derivative of y cubed, right, y of x cubed, I do the chain rule, bring the 3 down, reduce the exponent by 2, and then multiply by the derivative of the inside. So it might be more helpful if you think of taking d dx instead of just y cubed, think of it as d dx of y of x. cubed, because y is a function of x. And then you have to apply the power rule to the whole thing. And then you have to multiply by the derivative of the inside function. And the derivative of y of x would be dy dx, or y prime. So it's the chain rule, and it's because y is a function of x. So you apply the rule, the outer rule, to y, and then you have to multiply by the inner function, which is y. Okay, so that's my left-hand side. And then my right-hand side, the d dx of 3xy. So I'm going to give you a little hint. Put a dot in between the 3x and the y. I'm going to have to use the product rule on my 3x times y. 3x is a function of x, and y is a function of x. So I'm going to use the product rule, which would say first 3x times the derivative of the second. And what's the derivative of y? 1 times y prime, or just y prime. Yep. First times the derivative of the second, plus the second times the derivative of the first. So I've taken d dx of both sides, and now I just need to solve this thing for y prime. I want to solve for the derivative of y. Because if I have y prime, then I can plug in the point 3/2 and get the slope. So I want to collect any term that has a y prime on the left and any term that doesn't, put it on the right. So I've got 3y squared times y prime minus 3xy prime equals 3y minus 3x squared. All right, now what should I do? Trying to solve for y prime. Factor out the y prime. Great. So I have y prime times 3y squared minus 3x equals 3y minus 3x squared. And then divide both sides by 3y squared minus 3x. So we get y prime is equal to 3y minus 3x squared over 3y squared minus 3x. So what I need to find the equation of the tangent line is y prime evaluated at the point 3/2. So plug in 3/2 for x and 3/2 for y. Evaluated at 3/2. I'm kind of mixing notations here. So I'll get my calculator to do this for me. Okay, so 3 times 3/2. 3 times 1.5 minus 3 times 1.5 squared. That's all in the numerator. And then divided by 3 times 1.5 squared minus 3 times 1.5. -1. Does that jive with the picture that we drew? Yeah, the slope of that tangent line does look like -1. Okay, so I have a slope. The slope of this guy, I now know, is -1. So to find the equation of the tangent line, I'm just going to use point slope form because I don't have to do any more work. I have y minus 3/2 is equal to -1 times x minus 3/2. And if you are like married to y equals mx plus b, you could just distribute your -1 and add 3/2 to both sides. And you would get y equals -x plus 3/2 plus 6/2, which is 3. Either of these would be fine. So the process for finding the equation of a tangent line is exactly the same as it always has been. You need a point, and you need the derivative at the point to give you the slope. Finding the derivative at the point just has a slightly different approach now. It's called implicit differentiation. So this particular curve is called the Volume of Descartes. Kind of a famous curve. If you have an equation that cannot be solved explicitly for y, or even if it can be, you can still use implicit differentiation, and sometimes it saves you a lot of work. We say that the equation is defined implicitly, and the technique we just used is called implicit differentiation, where you take the derivative of both sides. So how do you know that you need to use this technique? The equation has all the x's and y's all jumbled together, making it difficult to solve for y. If not impossible, then very messy. So for example, if I want to find dy dx for the equation x equals y squared plus 1, I could solve this thing for y, but it would be messy, and I would have two different equations, right? I would have plus or minus the square root of x minus 1. So I'd have to take two separate derivatives, one for positive and one for negative square root. Or I could use implicit differentiation. So if I were to use implicit differentiation, I would take d dx of both sides. d dx of x equals d dx of y squared plus 1. All right, start on the left. What is d dx of x? 1. So the derivative with respect to x of x is just 1. That's simple derivative like we've always been doing. All right, now I want d dx of y squared. Right, so my derivative variable is x, but I have a y here. So y is a function of x, so I'm going to have to use the chain rule. So I apply the power rule to the y, and I get 2y. But then I have to multiply by the derivative of the inside function. The inside function is y. Its derivative is y prime, or dy dx. And then what's d dx of 1? 0. Okay. So I end up with this equation, 1 equals 2y times y prime. I solve it for y prime, and I get 1 over 2y. So when differentiating implicitly, just remember that whenever you're taking a derivative of a term that has a y in it, multiply that derivative by dy dx, or y prime, from the chain rule. All right, so let's say I want to take a derivative of both sides of this equation. We're not going to solve for dy dx just because it's going to be messy, but just for practice, taking d dx of both sides. I want to take d dx of the sine of x over y, and that's going to be equal to d dx of the ln of 3y squared. Oh, to the 5th, thank you. Oops. The heck? Okay, so d dx of the sine of x over y. So this is the derivative of the sine of some stuff. What is the derivative of the sine of some stuff? Cosine of the stuff times the derivative d dx of the stuff, which is x over y. Okay, so I'm just doing one step at a time here. The derivative of the sine of some stuff is the cosine of that stuff times the derivative of the stuff. And then how about the derivative of the ln of some stuff? 1 over the stuff times the derivative of the stuff. So this is going to be 1 over 3y to the 5th times the derivative of 3y to the 5th. Okay, so now I'm going to work on the two derivatives that I have left here. So I have the cosine of x over y. Okay, now I want to take the derivative of x over y. How am I going to do that? Quotient rule, yeah. This is two functions, x and y is also a function of x. So I have a quotient. So I'm going to have denominator times the derivative of the numerator, which is what? Derivative of x is 1, minus the numerator times the derivative of the denominator. What's the derivative of y? Y prime. All over the denominator squared. Okay, that equals 1 over 3y to the 5th times the derivative of 3y to the 5th. What would that be? 15y to the 4th times y prime. And then we're not going to solve for y prime here. This is just a practice taking the derivative of both sides. This is too ugly to solve for y prime. All right, so now I want you to try. Okay, so I've given you 4 famous curves, and I want you to find dy dx. And for some of them, you're going to use that to find the equation of a tangent line. Some you're just finding dy dx.